Good afternoon and welcome to the next session of the quantum computing lecture. Hope you're doing well, and we're progressing very rapidly with this course. So there are a few updates on the organization of the course that I also shared in iLearn. Next week, the lecture will not take place because I'll be away next week. But I also informed you which document you should read for or during next week while I'm away. Next week, you should read this document here, The Limits of Quantum, which is part of the theoretical computer science chapter. That one is available in Nextcloud. It's a couple of pages, something like 8 pages or something. I don't know the exact number. And feel free or you should read it. It provides you with initially a very quick overview about quantum computing, and then goes very much into theoretical questions about complexity and how powerful quantum computers are and so forth. Complexity classes, take a look at it. Will take you some time to read and understand it, but I think it's a very good paper. It appeared like in 2008, so 15 years have passed since then, but a lot has happened. Now we have real quantum computers available. In 2008, that was not really the case, and the ones we have today are obviously limited, but there has been progress, but obviously the theory will not change. So take a look at that. It's a very good document and should provide you with more insights about theoretical computer science. We will briefly discuss it next week, but you're really supposed to read it. And the second organization thing is, so the first thing is next week we don't meet, so we'll meet in 2 weeks again at the same time. And today the lecture will take longer. Horst Kuhnhardt, he will teach chapter 8, Quantum Computers and Programming. And since he's the vice president of our university, it was a little bit difficult to find a date when he's actually free. We only found a few dates sometime in mid of December, but by then you should actually be working on your seminar presentations. And that's why he will give his lecture today. He will join today around 4:30 and he will teach until around 6. So today's lecture will take a little longer than usual, and Horst will take about physical realizations of quantum computers, decoherence, and various architectures like quantum annealing, adiabatic quantum computing, and other architectures. So that's what he will do today. So we have to swap a few chapters a little bit, but it's simply because of Horst's schedule that is quite tricky this term, and we asked for your understanding. But we'll make sure that you will be able to understand chapter 8 without having done chapter 6 or 7. So all of that should be fine. And last week, we started looking at chapter 5, architecture. Concretely, we started with bits and qubits before we finished the quantum theory chapter. And then last week, we looked at bits and qubits, which we will now quickly revise. And then we'll go ahead with this chapter. Our goal is to figure out what are the fundamental quantum operations we can do in a quantum computer. Like in a traditional computer, we have Boolean logic gates and or not, but in a quantum computer, there are different gates. We'll explore them, but in order to understand them and to be able to describe that in terms of matrix operations, we first need to revisit our classical gates that we know from traditional computing. We'll try to describe them in matrices and then see how we can actually achieve so-called reversible gates, which are very linked to the unitary matrices. And then we have all the work in order to build quantum gates. And we'll see those most fundamental operations that we will then be able to use in quantum algorithms in the following chapter. And then Horst will give his part in between about how real quantum computers would actually work. So that's the roadmap for the next few chapters. And last week, we also looked at classic bits, which are either 0 and 1. We can also use our cat or vector notation for that. And we looked at that, and then we made a link to the quantum world, and we introduced the qubit. And a qubit is a quantum bit, which is not just either 0 or 1, but it's in both 0 and 1 with a certain amplitude, which are C0 and C1. And so we describe here a quantum state with our general rule that applies to quantum states. And C0 and C1 are complex numbers. We also briefly talked about measurements, because we measure a qubit, and when we turn it from a quantum state into a classic state, it will be either 0 or 1. And that's the measurement, which also introduces uncertainty, as we discussed last week. And then there are various notations how you can write a qubit. They're all equivalent, but it's just various notations. You should be familiar with all of them. We looked at them, and there's also an example, and we saw some further notations, and something like this here will be quite common. So that's what it means. It's an equal superposition, a qubit that is equally in 0 ket and 1 ket. And we need this normalizer in order to make sure that these two complex numbers, which are 1 and 1, add up eventually for this rule we have for quantum states. And that's why we need to normalize. And all of these notations here are equivalent. You will simply see this last notation from time to time now, so you should know what it means. And we'll need this equal, or today we will also see a quantum gate that can create equal superpositions, the so-called Hadamard gate. And that's one of the building blocks of a lot of quantum algorithms that we see in the following chapter. So we're now fully in the quantum computing world. Last week, we still looked at quantum mechanics, and from now on, we'll use all of that in order to build or to do quantum computing. First of all, I want to know from you if you have any questions about what we did last week. If there is anything, maybe just raise your hand here in Zoom, and we can discuss your question. If you don't have any questions, maybe just send a green sticker or something, and I'll see how you're doing. So as there are qubits, we need in a traditional computer more than just a single bit. In a traditional computer, we often think in terms of bytes. A byte are 8-bit. And like there is a byte, there's also a quantum byte, a so-called qubit, and that's 8 qubits combined. And we need this in order to this approach in order to generalize our concept of a superposition, because we said a superposition of a qubit is the qubit is partially in the state 0 and partially in the state 1 at the same time. And as we do that, we can have a superposition. But I also said in one of the last lectures, if we have a lot of bits interconnected, then we actually create a massive superposition, and we are at the same time in many, many different states. And this will allow us to get massive speedups through a quantum computer and using quantum algorithms for specific problems. And a qubit would therefore be a byte of qubits, so a quantum byte or qubit. And we can also write down our qubit in terms of a vector. And since we have 2 to the 8 many elements, we have 256 elements, then our vector that represents the qubit would have 256 elements. Each of those elements is a complex number. And we start with C0, C1 up to C255. And as I've put these comments here on the left in bold, that means that each of these entries refers to a specific value of our qubit. So the first one would be the value 0, the next one would be value 1, then value 2, or value 106. And for each of these values, we have a corresponding complex number. And so this is now 256 elements. It's still one quantum state. And our requirement, our constraint for quantum states is still then when we sum up the modulus squared of each of these amplitudes, it must be 1. Like for a classic qubit, which just has C0 and C1, we said C0 modulus squared plus C1 modulus squared must be 1. And now our states simply have 256 elements. And then this still applies that all of these modulus squares need to add up to 1. And such a qubit is extremely helpful. And we can not only just have 8 qubits that we could connect much more qubits, and then have even much more states that we can explore in a quantum algorithm at the same time. Now, for that, in order for this to work for sufficiently many qubits, we really need a quantum computer, because with a traditional computer, we can simulate this for a qubit. That's fine. We can emulate it, which will be slower than in a traditional computer. It will be slower than in a quantum computer, but we can still emulate it. But now imagine we want to have like a 64 qubit register, and then we will actually run into quite a big problem, because if we have a 64 qubit register, so not just an 8 register, but actually, so an 8 register would be just our qubit, but a 64 qubit register, we would need 2 to the 64 many complex numbers in order to represent such a 64 qubit register. And that would actually be a huge number of complex number we would need in order to emulate such a 64 qubit register. And that's beyond our current storage capability, because we just have a massive number of complex numbers. And now imagine you even want to increase this to 128, then you're also totally lost. So we see even just a 64 qubit register is something we're unable to simulate in a traditional computer. And this exponential growth is enormous. And this is why Richard Feynman actually came up with the concept of quantum computing. So we have actually a quantum computer which has 64 qubits, and we would then be able to actually run this. Depending on how to physically build it, that's another question. So Feynman only had a theoretical concept, but he suggested this. And actually, it's a pretty cool thing. Now, with larger quantum computers becoming available, this is becoming a reality. There are some architectures that have more than 64 qubits, some have less, and some are more general, some are less general, but that's a different topic. But in order to emulate something like this, you're totally lost with a traditional computer, but you'll be able to do this with a real quantum computer that has that many qubits. So that's certainly something very interesting, and that's what motivated Feynman to advance with the theory of quantum computing a couple of decades ago. Now, we can also wonder if we just have 2 qubits that we actually connect. So we have a pair of qubits, not 8, just 2 for now. We can say, well, our first qubit is a 0 ket. So that means our first qubit is in a state 0, and the other qubit is a 1 ket. So the second qubit is in state 1. Now, this is, as you remember, the tensor product. So we would, if we combine 2 qubits, we would write this pair actually as such a tensor product. However, if you always keep writing it that way, it's quite tedious to write this. So there are various simpler notations, but they all mean the same. So we'll just briefly look at them. You can fully write it out, 0 ket and 1, and take a tensor product. You could also just simplify this, which still means the same. It's just a little bit easier to write. It's a 0 and a 1 tensor product, and then a qubit. Sometimes it's also just written as a 0 ket, a 1 ket. Sometimes it's written as a 0, 1 ket, or just as a 0, 1 ket. This all means the same. It just is denoted in a different way, and it's probably simpler to read and write. So often from now on, if you see something like this, a 0, 1 ket, what it actually means is it's the first qubit, which is in state 0, and the next one is in 1. And actually, if you fully write it out, it would look like something like that. Then we can also represent this pair of qubits as a vector. It's more or less just the same as what we did before for the qubit, but the qubit was more general, and for 8 many qubits. Now for our pair of qubits, we can simply just write it out like this. It's a 4-row vector. So it's a column vector with 4 elements or 4 rows. And we have the 4 elements, and the comment is again 0, 0, 0, 1, 1, 0, or 1, 1. And since we said the first qubit is a 0 and the next qubit is in a 1, we would then put in the second element a 1 here and say, this is also how we can just express what we have expressed here. So all these notations, they all mean exactly the same. And I could also just write it out as a vector, and I get something like that. So you will see different ways of denoting this, both in this class as well as when you prepare your seminar presentation, and maybe sometimes you'll see something like this, something like that, or that, and then you all know what it means because it all means exactly the same. Then, in order to make this a little bit more interactive, I will quickly switch to my iPad and also interactively develop some of this. Then we can also say we have a pair of qubits, and just wait a second. Now my pen works. I could also write out something like this. 1 divided by the square root of 3 is the constant factor, and I'll have a 1, a 0, a -1, and a 1. And this can also be written out again in many different ways, just using these notations from before. We could, for example, just break this up and say, well, there is a 0, 0 ket component. There is a 1, 0 ket component, and there's a 1, 1 ket component. So just as the commons, this would be 0, 0, 0, 1, 1, 0, 1, 1. And we then have to move these factors in front. This would mean exactly the same as before. And we can again try to simplify it and say 0, 0 ket plus 1, 0 ket plus 1, 1 ket. And we just have then a fraction and put the square root of 3 into the denominator. And that's there was unfortunately a small mistake that I just noticed in the slide. It's correct. I had copied this wrong, but now we can fix it. There's a minus here, so we have to put the minus here, and we also move the minus here. Now it's correct. So the sign works, and it's just another way of writing this out. And if you have a general state of a 2-qubit system, so we have a general state of a 2-qubit system, we could, for example, say we have the 0, 0 ket, we have the 0, 1 ket, 1, 0 ket, and the 1, 1 ket. And then we have these complex amplitudes C0, 0, C0, 1, C1, 0, and C1, 1. So this would be the general state of a 2-qubit system. And as you see, the one above is just a concrete instance. Oftentimes, when you look into the literature or the book, you will also see something that may look like this. So we have a 1, 1 ket plus a 0, 0 ket, and we have this constant factor. Obviously, we can break it up and write it as something like this. And this two qubit system is actually very special because it is entangled. So here, the two qubits are entangled. Entanglement is also something we started to discuss last week, and entanglement is a special property of different quantum systems. And so each qubit here would be a system. And actually, what this means here, for this concrete example, we have a 1, 1 and a 0, 0. We don't have a 0, 1 or 1, 0. And actually, this two qubit quantum system is entangled. And what happens is, if we measure one of the qubits, for example, we measure the first qubit, and we measure a 1, then we automatically know the second, or we automatically know or measure that the next qubit is also a 1, because if the first qubit is a 1, we only have that option left that the second qubit is a 1, because it cannot be 0, because we just have 1, 1 and 0, 0. The same, if you measure the first qubit and you get measured a 0, then you know the second qubit must also be 0. So this is an entangled 2-qubit system, while, for example, the one here before is definitely not entangled, because we have a 0, 0, a 1, 1, but we also have a 1, 0. So these two systems here are not entangled, but the one we just discussed, they are. Yeah, there was a question here, if there should be a minus, maybe the one who commented it can, like Alexandra, you asked if there should be a minus somewhere. Maybe you can just turn on your microphone and point me to what you're referring to exactly.
Yes, I'm saying about the what is in between in the middle.
You mean this general one here?
Yes, the general.
Yeah, so these are all pluses, because it's just general, it's just an abstract description. And obviously some of these complex numbers can be negative, but then it would just be a negative value and would be like a minus. So this is just a general description. Is that fine, or you still have a question?
Yes, okay, thank you.
Okay, good. Then it's resolved. There's a question if like a 1, 0 or 0, 1 would be entangled. No, in this case, only here it's entangled. Or I think I know what you mean. If you have something like this, yeah, that could also be an example for entanglement. So this was the second question, because if you measure the 0, you know it's a 1. If you measure a 1, it's a 0. So that would also be an example of entanglement, but probably it's less commonly used. So the one here is more commonly used as a demonstration. But the other one, yes, would also refer to that. Now, we are actually done with the introductions to qubits and qubits. And our goal for today is to discuss quantum gates. And our quantum gates will be operations that are described by unitary matrices. So we need matrices to describe the quantum operations. But to make it there, we actually, in order to make it there, we need to look at our classical gates first, classical Boolean logic gates, and we will try to describe them in terms of matrices and how we can connect multiple of these gates, which operations we need. And once we have done this, we can apply the same concept to quantum circuits. There is a third question we got here in a chat with the mechanism we just described, that we have a 2-qubit system. If this can also be done with a 3-qubit system, yes, absolutely. So you would have a 0, 0, 0 ket, a 0, 0, 1 ket. That's absolutely fine. And we'll be dealing with such kind of stuff also later when we deal with quantum gates, because some quantum gates will, for example, have 3 inputs. And then we would be dealing with exactly that, because we need 3 qubits. But you'll see that later. So our goal is now that we just go back to actually one of the first few weeks of a computer science program in your undergrad, where you learned about classical logic gates, and we will try to describe them just in a very different way how you learned it in your undergrad. And that mechanism will then help us to work very well on quantum gates as well. Concretely, we'll be using matrices, and we will now look at our classic gates and try to describe them in terms of matrices. The simplest classic gate that we know is a NOT gate, and a NOT gate just in words. So if I put in a 0, I get a 1. If I put in a 1, I get a 0. And I can describe that as a matrix. I can write the NOT gate is, and it's the same mechanism as before. So rows are for the outputs and inputs are the columns. So if I put in a 1, I get a 0. If I put in a 0, I get a 1. And this is how I would describe a classic NOT gate. The NOT gate also exists in quantum computing, by the way, which just inverts the 2 amplitudes. But that's something we'll see later. We'll now look at the classic Boolean NOT gate. This is how we can write it. And we can also use an example for it. So we have our NOT gate, which is the matrix. And as you know from one of the first lectures a few weeks ago, we have the operation, the matrix, and from the right, we multiply the column vector, and then we get the result. And I have a 1, 0. That means this vector here represents a 0 ket. And I multiply the 0 ket with the matrix, and I get a 1 ket, because the second entry is now a 1. So I can also just write this out in a different way. I can say the NOT gate is the matrix. I multiply from the right a 0 ket, and I get a 1 ket. When you look at the NOT gate in quantum computing, which works like this as well, in quantum computing, the NOT gate is often called an X gate, but here we're just dealing with the classic Boolean gates. I will now develop on the iPad a few more classic gates that we know from Boolean logic, and we'll actually see how they work. So the next one is the AND gate. And the AND gate, we can quickly do the logic here, just which you're all familiar with. We have two variables, two inputs, x1, x2, and only when both inputs are 1, we get a 1, otherwise the output is 0. So this is the classic Boolean table. We can also try to draw the AND gate, the different ways how people write an AND gate. So in Europe, we have something like this. It's more common. We put an AND there or write AND in it. In the US, they use often a different notation, which I rarely use, but that's more like the US notation for an AND gate. And now we can think about how can we write an AND gate in terms of a matrix. We can say, well, the AND gate is a matrix, and I'll put the comments here. We have outputs 0 and 1, and we have 4 possible inputs, which is 0, 0, 0, 1, 1, 0, or 1, 1. And when I put in a 0, 0, a 0, 1, 1, 0, my output will always be a 0. So I put the ones here, because the output will be 0 for one of these 3 inputs. And if I put in a 1, 1, my output will be a 1. And this is a matrix way of describing our AND gate, because we have 4 possible inputs, 2 outputs, and we've just put in the 0 and 1s in order to get the output we want. Are you okay with that new notation for our AND gate that you know for such a long time now? Maybe just a green sticker if it's okay, or if there are any questions, please ask. Maybe some more, so looks fine. Good. We can also do an example. We put our AND gate here. So we put the AND gate, and I'll just copy it again. And we multiply this with a state. So we need 2 bits. So what we are writing now is not about qubits, it's just bits. Actually, but we can use our notation we have used so far. And what I'm actually writing here is I have an AND operation, and I multiply it with a 1, 1 cat. That's why I have the 1 here, and the others are 0. And I can now just do the matrix multiplication. So if I multiply or take the Cartesian product of the first row and the column, I will get a 0. If I do the second row and the column, I get a 1. So the output is now, it's actually a 1 cat, because I put in the 1, 1 cat multiplied, I put this into the AND gate, and I get a 1 cat, and this here is equivalent. So this is one example of how to deal with the AND gate. And as we have done this now for the AND gate, we can also do this for the OR gate. And do exactly the same. Remember, we have 2 inputs, x1, x2, 0, 0, 0, 1, 1, 0, 1, 1. And the OR will be 1 if at least one of the inputs is 1. So these last 3 will be 1. And just when both inputs are 0, the output is 0. How to draw the OR gate? Sometimes people write like or write other ways. In the US, there's again some notation that looks a little bit like this to write the OR gate. I'm curious for the international, or about the international students, or maybe all students, which notation are you more comfortable with, like the European notation or the US notation? Maybe just send this in the chat, which one you've seen more often, or the one you're dealing with, because we also have quite a lot of international students. And I feel here in Germany, we probably don't see the US notation too often in at least German language books. So seems to be some slight majority for the US. I personally prefer this EU or European notation because I just learned it that way. I rarely myself use the US notation, and only when I see it in a paper or book, I actually use it. Then we can also think about how can we write the OR as a matrix. Same scheme as before, outputs 0 and 1, inputs 0, 0, 0, 1, 1, 0, 1, 1. And here we only want a 0 if both inputs are 0, so we put a 1 there in order to say yes. If I put in that input, I get a 0. And for the other 3 inputs, I want output 1. And this is how I write my OR gate in matrix notation. And we can do again a quick example. Something like this, for example, and we can again do the multiplication of the matrix with this vector, and it will be 0, 1, because if we take this row and this column, it's 0, and this row and the column is 1. And we can also write this out. Again, we can say the OR gate, it's a 1, 0 ket, and this will lead to a 1 ket. So this is just using our ket notation to write it out. So now we have the NOT gate, the AND, and the OR gate, and we have actually described all the fundamental Boolean gates that we need. And from them, we can build more complex gates, more complex circuits. And how to do this with classical gates is something we'll discuss now for the next, I don't know, half an hour or 1 hour. And once we have this, we can do more or less exactly the same, just with quantum gates, for which we have other gates available. But it's more or less the same concept over and over. Now, we also advance now by building a different gate, which is called the NAND gate. So the NAND gate means we have an and after this, we put a negation, which is this part here. And now we could think about how do I build actually this table or this matrix in order to do that. But here comes the interesting part. I don't need to come up with this matrix myself. I can actually just come up with the matrix by multiplying 2 matrices that I know. So what I'm doing is I have an AND gate, and after the AND, I'm doing a NOT. And remember, the order is, say, I would multiply some vector from the right with and after this, I'm doing a NOT. But I don't need to do it in this order. In order to build an AND gate, what I can actually do is I have an AND gate, and since the NOT comes after the AND, I multiply the NOT from the left, and I'm multiplying these 2 matrices in order to get a matrix that represents the NAND gate. And these fundamental matrices we have seen, NOT was 0, 1, 1, 0, and the AND gate was the one we did before, all 1 and then a 0, and then all 0 and then a 1. And now I'm just multiplying these 2 matrices, and you all know how to multiply matrices. So maybe quickly take some time to multiply these matrices. And once you have the answer, send your matrices here to the chat, maybe without looking at the slides, because the answer is there. And then we have actually a matrix that represents the NAND gate. So please go ahead multiplying these matrices and send me your new matrix. And for the NAND matrix, I'm also putting the comments here, just the comments to see what the inputs would be. And then once you have these matrices, send them here. So there've been various suggestions. The ones I've looked at, they look correct. We can quickly start it. So we say we have this row and this column. This is a 0. We have the column and the next row, it's a 1. And if you actually continue this process that you multiply these two matrices, what you will get is something like this. Now it doesn't fully match with the comments, so I just move the comments and move them to the right place, and it fits. So this is actually our NAND gate, and we built it by taking an AND matrix and then after it multiply from the left the NOT gate. In the answers I saw in the chat, they also look reasonable. So this is what we just did. And like this, we can chain more operations and eventually get our gate. All we need to do are matrix multiplications. Now, in terms of the theory, if I have a gate, some logic gate A, and I have m many input bits and n many output bits, since a bit is either 0 or 1, I need to raise this to the power of 2. So if I have m many input bits and n many output bits, I will have a matrix that is of size 2 to the n by 2 to the m. So 2 to the m is the input, the number of columns, and the number of rows is 2 to the n. If you remember our gate from just before, it had one output bit. So 2 to the 1 is just 2. So 2 rows, and 2 to the 2, because we had 2 inputs, 4 many columns. So this is the general scheme we'll be dealing with. And we will now actually continue a little bit, trying to build more complex circuits with multiple gates that also run in parallel, not just in sequence. And then we can actually do the same just with quantum bits, with quantum gates later. But first we'll continue with the sequence. So if we have in sequence a logic gate A and then a logic gate B, that's also what just more or less what we did with the NAND gate. We can say we have m many inputs, n many outputs of A, and then we have p many outputs of B. I can represent this as a matrix multiplication. So I first do matrix A, then I do matrix B. So I multiply B from the left. And matrix B has p many outputs, so it's 2 to the p many rows and 2 to the n many columns, because n many inputs. And for A, we have m many inputs and n many outputs, so we have a 2 to the n by 2 to the m matrix. And as you know, if I multiply these two matrices, so a 2 to the p by a 2 to the n matrix multiplied with a 2 to the n by 2 to the m, it's a 2 to the p by 2 to the m. So we can represent this as one operation by just doing the matrix multiplication, and that's just what we did for our NAND gate. And now this is here generic. Good. It becomes a little bit more difficult if I have logic gates that are not in sequence but in parallel. So I have gate A with m many inputs and n many outputs, and I have gate B in parallel with m prime many inputs and n prime many outputs. And it turns out I can describe this very well with a mechanism that we have learned in the past, which is the tensor product. In order to build a matrix that represents these two operations running in parallel, all I will need is a tensor product. For A, I have a matrix. For B, I have a matrix, and I just take the tensor product, and this will lead actually to my output. Down here is also a generalization of what the size of this tensor product matrix would be, but feel free to look this up at home. I'm not reading out now n prime, m prime. It's probably better to see this in writing, and feel free to try to generalize this at home. Or all you need to know is I just take the tensor product of these two matrices in order to describe this here. This is the next one. And now we can actually say, well, we not just have things either in sequence or things either in parallel. I can combine parallel and sequential operations. And I have a sample circuit here. And what that circuit would look like is I have a gate A, and A has n many inputs. So all the n inputs go into A. And then A has p many outputs that go in gate B. For B, I have q many outputs. You know how to describe this, at least gate B, because for gate B, I have q many outputs and p many inputs. Gate A is a little bit more tricky because not all outputs of A go into B, but some of them stay in parallel to B. And now comes the question how to describe this. I can say, well, if P many outputs of A go in B, I have some left, and I can say, well, these are M minus P many outputs that I have left that don't go into A. And I can try to describe this now in terms of matrices. I can say, well, A is a 2 to the m by 2 to the n matrix, because I have n many inputs and m many outputs, but p many of these outputs go as inputs into B, and I can describe B as a 2 to the q by 2 to the p matrix, because I have q many outputs and p many inputs. And then I have these m minus p left that don't go into B. And as we don't want to treat these remaining m minus p bits, we can describe, since we just don't want to change them, we just want to keep this. If you need an operation that doesn't make any changes to these bits, all we need is an identity matrix. So we need an identity matrix of 2 to the m minus p by 2 to the m minus p many elements. And the identity matrix is called I. So I can call this, if I have m many p elements or rows in there, I can say, well, it's I, and the subindex is m minus p. And now I want to describe all of this as one matrix. And what I need to do is, I have my operation A, which comes first. It's this one. And then I need to multiply this, not just with B, because B is part of what follows, but what follows is also that I don't change m minus p many bits. So these m minus p many bits just stay in parallel to B. And if something stays in parallel, we use the tensor product. So I use the tensor product of B and I, M minus P. This part describes what I've just highlighted, the right part. And since the right part comes after the left part, I first take A and I multiply the tensor product from the left. Looks abstract and complex, but actually we've just built this step by step. So we say for parallel elements or parallel bits, we use the tensor product. For sequential ones, we use the matrix multiplication. And now we will actually try this together in a bigger circuit and build this step by step. And for this, I'm moving back to the whiteboard. And what I want is a sample circuit. The sample circuit is also in the slides. I have a NOT gate. I have an AND gate. And then their outputs will both go into a NOT gate, an OR gate. So this is my OR gate. I'm just writing the comments to them in case it's not drawn too well. So this is the OR gate. I have 3 gates, and now I want to describe all of this as in terms of one matrix. We know what the OR gate looks like, so that's the easy part. And we'll focus first on the left part and build this. And for the left part, what we need is we have a NOT gate, and we need the tensor product with an AND. And our NOT gate looks like this. We have the tensor product with AND, and the AND looked like this, as we saw. And what we need now is simply a tensor product. And the tensor product is something we had learned before. It will lead now to a substantially larger matrix. I'm also quickly adding the comments just to make sure we are on the same page. Feel free to try doing this tensor product on your own. We've looked in the course in how the tensor product works, but I can also just derive it or derive the solution here. So 0, 0, 0, and this was one of the questions before, if we can also do this mechanism with 3 bits or qubits, whatever. Yes, we can. So we have 0, 0, 0 because we have these 3 inputs. And then the next one is 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, and I'll move this back. So we have 2, 4, 6, 8 many entries. And now you can find this result by doing the tensor product. The first 4 here are all 0 because of this 0. So 0, 0, 0, 0, 0, 0, 0, 0. The same applies to the next or to the last block because there is a 0. So 0, 0, 0, 0, and more zeros. Then we have these. So I'm just putting in the blocks to make this visually more understanding. Here we have a 1 and here we have a 1, so we just copy paste. the matrix from the right. So 1, 1, 1, 0. And these zeros here. And for the last block, it's just the same. 1, 1, 1, 0, 0, 0, 0, 1. Yeah, so that's what it looks like. And this tensor product is now describing the left part that I highlighted here in blue. I have an AND and a NOT in parallel. And now I need to think about the OR gate. And actually the OR gate comes after NOT and AND were in parallel. So what my result would be is OR, I multiply from the left with this NOT tensor product and AND. You know what the OR gate looks like. We have this part up here. Feel free to do this matrix multiplication on your own, how to multiply this big matrix with OR. I also have the result available for you. It's also in a slide, so I will just copy and paste the result. And I'm not doing this matrix multiplication because it will take probably forever. So I'm just putting the comments here again. And the result would be we have 0, 0, 0, 0, 1, 1, 1, 0, and then 4 ones and 0, 0, 0, 1. This would actually be the matrix describing our whole circuit. And what we need to put in is a state vector that represents a concrete value from here. Since we have 3 bits, we have 2 to the 3 many elements in our row vector, so 8 many elements. So we could multiply some vector here from the right, which has 8 many elements, and we would then get the result if it's 0 or 1. So this is maybe a new way for you to see how we can think about Boolean logic. We're actually just thinking in terms of matrix operations, multiplications, tensor products, and so forth. And like this, we don't manually need to try out all the combinations step by step in order to come up with a logic table. Rather, what we can do is we can just come up with the final matrix, which represents this logic. Is this some approach that any one of you had seen before? How to describe, I mean, before looking into this course, how to describe Boolean logic? If you've ever seen something before taking this course, maybe send a green sticker. If you have never seen something like this before, a red one. So there's actually someone who saw this before that course. Maybe you can tell me where you saw this, if you saw this in a quantum computing course, or if you just saw this in an introduction to binary logic. Maybe you can just write me or write us in the chat where you had seen this before. I've only seen that approach when I looked into quantum computing later in my career. I didn't see that way of notating the Boolean logic when I was a first-year student, but probably it's an interesting approach which adds a little bit of complexity, but finally we can break everything down in terms of matrices and probably also make some stuff slightly more complex, some stuff simpler. It's just a different approach, but that approach will be needed now in this course when we start looking at quantum gates. And I'll move back to the slides now. So This is what I've just done with you on the whiteboard. So we had this circuit and came up with this matrix. Now, I said we want to build quantum gates, but actually for quantum gates, we want quantum gates to be reversible. And so we first need to look into reversible gates. I've addressed this issue or topic of reversible computing a while back. And I mentioned this when we talked about unitary matrices. I said we want to be able to undo operations. We've also seen the unitary matrices in the quantum theory chapter, when we saw how we can advance with operations, how we can undo. And now we also need to actually build this in terms of gates, which are more concrete, doing our operations. And we got an answer from a student, and she says in her first year at university, she had a course on computer and software engineering, and they had Boolean logic, and then saw this kind of matrix approach, how to describe Boolean logic. Well, that's good, but I guess from most answers, they didn't see this before. They only saw Boolean logic, obviously, in their first year introduction, but more from a logic perspective, not just from a purely matrix perspective. Yeah, now we'll look at our reversible gates, and reversible gates will be represented by unitary matrices. You remember unitary matrices, we've been dealing with them in this course ever since the course started. And we can now wonder, is the AND gate actually reversible? So we've looked today quite a lot at the classic AND gate, and actually the AND operation is not reversible. So reversible would mean you put inputs in your operation, you get your outputs, and then you could just sort of undo that operation. And a classic AND gate is obviously not reversible, because in a classic AND gate, I put in 2 bits and I get 1 bit out. And I lose information, and just from the output, I cannot ultimately infer what the input would have been. So the AND gate is not reversible. What we know is the NOT gate is clearly reversible, also in classic Boolean logic, because the NOT gate I can just apply to itself. And finally, if I apply the NOT gate to itself, I get the identity matrix, and the identity matrix just doesn't change anything. And I can also apply the identity matrix to itself. So multiply the identity matrix with itself, and I just get a new identity matrix, the same identity matrix. So the NOT gate and the identity gate are actually reversible. Now we will look at reversible gates. We will first of all still look at them from a Boolean perspective, so purely from a logic perspective, but we will introduce them. And once we have introduced them, we will see that these new gates we're introducing, they will also be able to be applicable to quantum computing or to quantum states. So first, we actually look at quantum gates, but we're not too interested that they are quantum gates. Actually, what we care about is that they are just reversible gates. And reversible would mean we can just undo the operations. And then we see that they can actually be also used for quantum states and not just for classical logic states. The first one we look at is the controlled NOT gate, which is also sometimes just called C-NOT. It's a controlled NOT, and I will now plot it, and then we discuss what it actually does. And it doesn't matter too much yet that it's actually a quantum gate. We'll just look at it from a logic perspective and see what it can do for us and why it's actually reversible. That's the next part that will come. If you want to see a very nice visualization of all of this, obviously look into the slides. My hand drawing skills aren't too great. So this is the C-NOT gate, and the C-NOT gate actually has 2 inputs and 2 outputs. We'll use this now purely from a logic perspective later for quantum. And the C-NOT gate is a controlled NOT gate, and it actually, the top input is called the control bit. We'll just talk about bits now because the quantum part will only come later. Now it's just a purely logic gate. And then I have 2 output bits, or 2 outputs, X and something else. Anyone knows what this sign stands for which operation? If you know it, maybe just send it to the chat, what that logic symbol means. I'll wait for you to send this to the chat and see who recognizes this logic symbol. So it has nothing to do with quantum yet. It's just logic. So I didn't get any responses yet. Maybe take some moment for you to send it. Maybe a green sticker if you recognize this logic symbol, or send a red sticker if you don't recognize this logic symbol. And we got the right answer. Yes, this is the XOR. We can here on the side quickly look at the XOR gate. Say we have inputs X and Y. Oops. And then XOR can be written with this plus and a circle around. It's an exclusive OR, so an either or. We'll look at the combinations. And the XOR is only true if these 2 inputs are different. So 0, 0 will lead to 0. A 1, 1 will lead to 0. And the 0, 1 will lead to a 1. And a 1, 0 will lead to a 1. So this is the logic operation we're applying here in this controlled NOT gate. And so what the controlled gate does is I have inputs X and Y. X is the control, Y is the value I'm putting in. The output X will be just the same as the input X. And the second output will be an XOR, so an XOR of X and Y. And what effectively happens is if X, so our control, is 0, then the output will be just Y. So if X is 0, we have this case here, X is 0, and we see the output will be just Y. If the control bit, however, is 1, then we're just inverting the input Y from 0, 1 to 1, 0. So if the control bit is 0, the second output is just Y. Otherwise, we just invert the second input. That's what it does. And in terms of our tensor product notation, we had looked before what the controlled gate does. Controlled NOT gate does is I have my XY ket, and this will be turned into X and X XOR Y ket. So I have my inputs X, Y, and the outputs are X, and the second output X XOR Y. Very importantly, the XOR, just a reminder here, the XOR is this plus with a circle. The tensor product is an X with a circle. So it looks slightly different but makes a huge difference. So don't forget that. I didn't come up with this notation. Simply the XOR is often denoted this way, and the tensor product is denoted this way. It looks almost the same, but makes a big difference. And we can now try to describe this as a matrix. We have 2 inputs and 2 outputs, so we need 4 rows and 4 columns because X and Y are binary. So we have 4 possible combinations of inputs and 4 possible combinations of outputs. We can try to describe this. We have inputs 0, 0, 0, 1, 1, 0, and 1, 1. And outputs 0, 0, 0, 1, 1, 0, 1, 1. The first 0 stands for an X, and the second 0 stands for the Y. So this is X and Y. And we said if the X is, or the X doesn't change, X is the input and X will be the output. And the second, the second output will be Y and maybe transformed through the XOR. So if X is 0, we said this XOR doesn't make a difference. So if the control bit is 0, the second output will be just Y. So I can put a 1 here, because if I put in the input 0, 0, the output will be 0, 0, because the X doesn't change. And the Y doesn't change either, because the control bit is 0. So a 0, 1 would also remain a 0, 1, because that's the input. Control is 0, input is 1. So the output is also 0, 1, because if the control bit is 0, it doesn't have any effect in the XOR. It becomes more interesting when the control bit is 1. And if the control bit is 1, we said we flip the second output. That means if we put in, if our control bit is 1 and the second input Y is 0, we flip that 0 to a 1. So this would be 1, 1. And if the control bit is 1 and the second input is 1, then that second output would be just flipped from 1 to 0. So we put in a 1 here. And these are the 4 combinations how we can transform the 2 outputs into, the 2 inputs into the outputs. All the other values in the matrix are just 0, because there's nothing else they do. So I'm just filling in the zeros. And this is how I describe my controlled NOT gate. What do you notice about the matrix? Is there any property you may notice about this matrix? If you have any suggestion what you notice about the matrix, maybe just raise your hand here in Zoom. Yeah, the one who raised the hand, maybe just turn on your microphone.
Okay, hello, can you hear me?
Yes, go ahead.
Okay, I do not know the name anymore, but all the columns and rows are 1.
Doubly stochastic matrix, is that what you mean?
Yes.
Yeah, okay, that's true. That's correct. We needed doubly stochastic matrices when we looked at probabilities. Yes. Right now we're not really dealing with probabilities. Any other suggestion? Maybe someone else notices something about this matrix? What property it may have? Richard, your microphone is still on. Okay, good. Now it's off. So we can actually if someone still wants to put on their microphone or something, please go ahead. Otherwise, I'll just go ahead. Well, we can try to multiply this matrix with itself. We can actually, or this is your task. I want you to, or let's say, yeah, we say this is C naught. And let's take a look at what's C naught dagger. Remember, the dagger is the adjoint matrix. And the adjoint matrix means we transpose the matrix and we flip the sign of the imaginary part of the complex number. But there are no complex numbers in here. It's just real components. So if I take the adjoint, this is just a C naught again, because the transpose doesn't affect these two, and these two get flipped, but they're just 1 and 1, and there's no imaginary part. So C naught and C naught, C naught dagger and C naught is the same. I want you to quickly multiply these two matrices with themselves, just C naught with C naught or C naught with C naught dagger. And once you have a suggestion what the result is, maybe send it to the chat. I'll also quickly start drafting this. Maybe you can already also try on your own to multiply these two matrices. And while I'll give you some time to try this, I'll try it in parallel too. So first row and first column is a 1. Then the other elements are just zeros in this row. Then we can take the second column and the second row. We have a 1. The other ones will also be 0. Then we can take the third row and the third column, which would lead to 1. And also for the fourth one leads to 1. And all the other elements will be 0. That means I have found the identity matrix. So I multiply C naught with itself and I get the identity matrix. So who remembers, we've talked about the name a few minutes ago. What's the property of our C naught matrix if multiplying it with its adjoint, so its dagger, leads to the identity matrix? What's the property of the C naught matrix then? Maybe send it to the chat or turn on your microphone. So C naught is, it's reversible, yes. So C naught is unitary. So remember, unitary means U dagger times U is the same as U times U dagger is the identity matrix. So that's the idea, or that's something we observe here. The C naught is actually a unitary matrix. And unitary matrices are key to quantum computing, because in quantum computing, we'll be dealing all the time with unitary matrices, so we can undo operations, which we will see later. So what it actually means is I have a C naught and multiply from this left a C naught. That would then mean, if I try to visualize this, so we can visualize C naught multiplied with a C naught, means I have my C naught from before. and we saw the first input doesn't change, and the other one we called X or Y. And this X C naught is this part. And now I apply another C naught. So I multiply from the left. So after this, I apply another C naught. The first input still doesn't change. So it's still an X. But the second output changes. And I can try to visualize this. So the input to the second or to the C naught here would be still my X. I'll just write it slightly different. Put it here. So the green part is the same, the X or Y, because this comes, so to say, from here to there. But I also have the control that comes in, and the control would be then an X or. As before, in the first C naught, I said, well, I had the input X, which went into the X or Y, because Y was that second input. Now we have the second C naught gate. The second input is the one I have highlighted in green, an X or Y. And that second input will have an XOR with the input, the first input again, an X. Now, I'm asking you, what is X or X? Classic Boolean logic. Anyone remembers this? This is classic Boolean logic. And while you think about this, I can visualize something. So that yellow part is of interest now. What it actually looks like, this yellow part, is I have my X or, and the green part would be X or Y. But the XOR operation is associative. So I can write this also in a slightly different way since it's associative. I can first do these XORs with X and itself, and then the XOR with Y. So now the question is, what is this part here? X or X. We can try to write it out. So we can say X and X are the two inputs to the XOR. And X is either 0 or 1. And if I apply the XOR to the two values that are the same, the output is 0. So X or X is 0. So this is 0, X or Y. And the 0 in an XOR is a neutral element. So I can just eliminate this. So the output is just Y. So we can simplify this and say, well, the output is just Y. That means if I apply the C naught gate to itself, it will just undo the first C naught gate. We have now looked at this from a logic perspective, and before we have looked at that from a matrix perspective. So the C naught just reverses itself. When we look at the matrix, the C naught gate is represented by a unitary matrix. We'll do a 5-minute break until 3:30 and then resume. So welcome back from the break. In addition to the C naught gate that we have just seen, so what you see here is what I had visualized on the iPad. Here it's just printed properly. There is another very important gate in terms of reversible gates. It's the Toffoli gate. And the Toffoli gate looks a little bit like the C0 gate. It's just slightly more complex. We have inputs X and Y and input Z. And we have two outputs, X, Y, and the last output is our output Z and an XOR of the AND of X and Y. So we have an XY and an X and a Y, and we have an XOR of that with the last input Z. So this is quite similar to the C0 gate, and the bottom bit Z only flips when X and Y are 1, because then this is 1, and we have a 1 XOR Z. This means we can flip the Z only if X and Y are 1. So we are taking the state XYZ to the state XY Z XOR X and Y. This is the idea of this gate. Just wait a second. I'll be back in 30 seconds. So sorry for the interruption. My kids just came home and I forgot to lock my office door, which I just had to do. Otherwise, I'm unable to stay focused on the class here. So this Toffoli gate can also be written in a matrix. And the matrix looks super complex, but it's actually quite similar to what we had done before. And I will not write down the matrix on my own on the iPad. But what I said is, we only have this flipping effect of the third input if the first two inputs are 1. So 0, 0 just stays 0, 0, because X and Y are the inputs that stay as outputs. And the Z is only flipped if X and Y are true. So X and Y are 0. The value, the third value doesn't get flipped. If these two are 1 and 0, they're not both 1, so the 0 doesn't get flipped. So 1, 0, 0 just stays 1, 0, 0. But we only get this flipping effect if X and Y are 1. Then this 0 of Z gets flipped from 0 to 1. So 1, 1, 0 gets flipped to 1, 1, 1. And 1, 1, 1 gets flipped to 1, 1, 0. So the two inputs, the first two inputs always stay as the same outputs. And the last input, Z, only gets flipped if X and Y are 1. So 1, 1, 0 is being turned to 1, 1, 1. And 1, 1, 1 is being turned into 1, 1, 0. Maybe just send a positive or negative reaction if this matrix is understandable then to you from what I've said. But it's just more or less the same as the C0, just slightly more complex. And okay, seems understandable. And this Toffoli gate is actually something we say it's universal. So we can use the Toffoli gate in various variations to make any logical gate. And we can do all reversible logic computing or binary logic computing purely with Toffoli gates. And the Toffoli gate, again, will obviously later be used for quantum states, not just binary states, but we're still in reversible computing, not in the quantum gates yet. But the quantum gates will come very, very soon. And the Toffoli gate is actually a quantum gate, so not just works on binary states, but on quantum states. And we can use various modifications of this now. I will quickly move to the whiteboard to discuss this with you. We have said the Toffoli gate is universal. And the Toffoli gate, remember, looks so. Yeah, X and Y as the two controls. And we had our Y, but I'm not writing in the Y. Not yet. X and Y stay the same. And we said that the output would be, if I put in the Z, it's a set XOR X and Y. This is the logical operation. Now, if I don't put a concrete, some abstract value set, but say a 0, then my Z is 0, and 0x or something is just the something, because set a 0x or something is just a neutral element. So this would then be simplified as X and Y, because this part will be just disappearing if my set is 0. So what I have done is I have built an AND gate from the Toffoli gate, because the last input is simply a 0, and the 0x or something just disappears, and I keep the something, and the something is the AND. So I have just built an AND gate from the Toffoli gate. The Toffoli gate can be used for other stuff. I can even combine multiple Toffoli gates. As you will see now, this would be a little bit of a bigger circuit because I'm using multiple Toffoli gates. So I have inputs X, Y. I put in my 0. So I'm just putting in what I have just done in a single Toffoli gate to build an AND gate. Remember, X and Y stay so far. And this one becomes X and Y as before. Now I have another input that I call Z. So usually the third one here we call the set, but the third input is not just a 0, so it doesn't have any name. And we have one more input, which we call a W. And now I'm adding another Toffoli gate. And what happens here is, so the X and Y just stays, because X and Y here is an input to the next Toffoli gate. This just stays. Set also stays. And now, what will be the output of my Toffoli gate? It's W XOR, I have this Z. So somehow this set plays into it, because this, before we said it's W XOR X and Y. So the first two inputs. Now the second input to the second Toffoli gate is this set. And the first input to this second Toffoli gate is this green part, X and Y. So I can say X and Y as the first input and the second input Z. So I have built now a larger Toffoli gate for 3 inputs that go into the AND and have an XOR with the fourth input. Now I notice one problem. What I have is, at the end of all of this, the input, so the X from the beginning stays, the Y stays, the Z stays, and I have this complex output which stays. But the input 0 that I put in, the one in green, is now turned, the input 0, it would be now the output X and Y. And that's not too cool, because what we've created is we've put in inputs X, Y, and Z, they don't change, but I put a 0, and the 0 turns into some new operation. And actually, the only thing I wanted was one specific output at the end. I didn't want to manipulate the other inputs. But this has happened because of the first Toffoli gate. And I don't want this. I actually want to keep this as a 0. Because it just doesn't look nice if this is turned, if the 0 input is turned into something different. And the way to fix this is to put in another Toffoli gate. Because as you remember, a Toffoli gate can undo itself. That's just what we had done before for the C0 gate. We said the C0 gate can undo itself. We've derived this for a long time. And the Toffoli gate, we've looked at its matrix, and the Toffoli gate is also a unitary matrix eventually. So if we apply the Toffoli gate to itself, we will just undo it. So this X and Y would just be undone and become a 0 again, because Toffoli gate just undoes itself if you put it in sequence. And I'm putting, so in total, a third Toffoli gate here just to undo this manipulation of this helper variable, because it's not good to transform these helper variables or input into something unexpected. All I wanted was the actual output, but I didn't want to change any of the helpers. And that's why I've put in one more Toffoli gate to undo what I had just done for the 0. I don't, with the third Toffoli gate, I don't change anything impacted by the second Toffoli gate. So my actual output I wanted, I still get, but I'm undoing something. And this is actually super important in quantum computing. I mentioned many times in this course, unitary matrices are key to all of this because they allow us to undo something. And in quantum computing, we really don't want just to use the first and second Toffoli gate and turn this 0 into something which is actually not part of our result. What I'm creating here, in fact, is I'm creating some unnecessary superposition in quantum computing. And this will lead to lots of trouble. It will actually make my computations much more complex and probably less certain. And that's why you will often see in quantum computing, when you have these intermediary helpers and you maybe turn a helper into something you didn't want, but it happened because of a gate, then you need to undo this partially so that you don't have this unnecessary superposition. And that's why we can always undo with unitary matrices, and that's why reversible computing and unitary matrices are so important. This is actually the best example to show this. And in a real experiment, you have much more than 5 variables, and then having such an unnecessary superposition would just lead to lots of problems in your computation, and that's why let's just undo it here again. We can also build other gates from the Toffoli gate, which I can demonstrate you in the slides. Will come in a second. So this was the 3 Toffoli gates we had just seen. We can build a NOT gate from Toffoli gates. We can put a 1 and a 1 as direct inputs, not a variable, but just fixed values in our set. You can try this out at home with Boolean logic. We will actually just invert the set. So that can be done from Toffoli gates, which seems to be very helpful. We can also use a Toffoli gate to create a fan out. So the inputs are 1, y, and 0. And you know now how the Toffoli gate works, so feel free to try this out at home. It will actually be turned into a 1 y. So we are sort of copying the y and have the y as an output twice. This is something we call a fan out. We can do this. Very importantly, the fan out only works with classic binary values. A fan out cannot be built from quantum states, as we will later see, but we're not officially in the quantum section yet. Right now, we're with the reversible gates. And since we only work with binary logic so far, we can build a fan out, so we can just copy or duplicate a value. This can be done. And then there is another gate that is described in the literature. It's called a Fredkin gate. The Fredkin gate is also a universal gate, like the Toffoli gate, works slightly different, but it's also universal. I'm not discussing it here in this course. It's in the slides, and also it's matrix, which is unitary, by the way, so it's also reversible. Feel free to study the Fredkin gate on your own. We have skipped it so far because we don't need it any further. We can just use the Toffoli gate. The Fredkin gate is just a slightly different gate, but that eventually is also universal and reversible. And you can build from the Fredkin gate, again, all the other gates, since it's universal, like an AND gate, a NOT gate, and so forth. But we're skipping the Fredkin gate. So now we have looked into our Toffoli gate, and we have now seen the Toffoli and C0 gates that are reversible. What I'm saying, or what is now in the slides, is some of the stuff we have already discussed. We said unitary matrices are super important, and we have actually talked about unitary matrices, I think, almost every week. And unitary matrices are the operators we need, or our operators that we will use in quantum gates are represented by unitary matrices because it allows us to undo operations. And why we need to undo, we've seen this before with these 2 Toffoli gates, and then we needed a third one. And quite a few gates we have seen today are actually quantum gates. The identity matrix is a quantum gate. The NOT gate, the C0 gate, Toffoli, and Fredkin. They can all be represented by unitary matrices, so they not just work on binary states, but also on quantum states. There are other quantum gates that we will look at now, and one of them is, for example, the Hadamard gate. We've seen the Hadamard gate, I think already in the first week when we looked into linear algebra, or complex linear algebra, but we had not called the Hadamard gate always a Hadamard gate. And we will now look at what the Hadamard gate actually does. For this, we'll switch back to the whiteboard. And the Hadamard gate is a very important quantum gate. We'll see very soon why, and it's key to, I think, almost every quantum algorithm. It's called H, or if you visualize a circuit, we often just write it like an H for the Hadamard gate. And the Hadamard gate is a matrix. Again, I'm just putting the commons there just to remember what all of this stands for. This matrix here, 1, 1, 1, minus 1, is not a unitary matrix because a constant factor is missing, and it's in fact this factor here, 1 divided by the square root of 2. Then the Hadamard gate is actually unitary. Feel free to try out at home if it's unitary and multiply it with its adjoint, but it is unitary. I can guarantee you this. And the Harder-Matt gate is so important because it allows us to create superpositions. We can try this out now. We can multiply our Harder-Matt gate with a classic state, which is 1, 0. 1, 0, as you remember, 1, 0 is just the 0 ket. And we'll see now what happens if we multiply them. So if we multiply them, we see there is a 1 divided by the square root of 2. And the next, because I have this one and this one, but this belongs here. So it's 1 divided by the square root of 2. And then I can continue this for the second row. So the column with the second row, and it's again a 1 and a 1 and a 0 and something, just 1 and a 1. So it's again a 1 divided by the square root of 2. And this is a state we had seen many times. This state here is actually our 0 ket plus 1 ket, and we have the normalizer of the square root of 2. This is something we did last week when we started looking into qubits. So what we see is the 0 ket is turned into a 0 plus 1 ket equal superposition. So this is an equal superposition. We're equally in 0 and 1. So what the Harder-Matt gate does, it's actually creating equal superpositions. So it turns classical values into superpositions. And when we work with a quantum computer and send values from outside, instructions, obviously from outside, we're sending classical values, because a classical computer that we use outside to control a quantum computer, the classic computer only works with binary states. And then we need to turn binary states into quantum states. And that's what the Harder-Matt gate does. The Harder-Matt gate can also turn the 1 ket into an equal superposition that we also saw last week. Looks like this. And since the Harder-Matt gate is unitary, remember, if you apply something like our classic state to the Harder-Matt gate, and you apply again the Harder-Matt gate to it, you're just undoing it. So it would again turn your equal superposition into your original classic value. So if you just apply it again or in sequence, without doing any other operations in between, obviously. So this is the idea of the Harder-Matt gate. It creates equal superpositions. And that's often the starting point in a quantum algorithm, because we come from outside, we have classic values that need to be turned into quantum states. And that's what the Harder-Matt gate does for us. It's something you will see in, I think, every quantum algorithm, because somehow we need to create our superpositions to get started. So this is what I had just visualized, how to turn 1 into the 0 minus 1 ket divided by the square root of 2. Feel free to try it out, that you just multiply the vectors 0, 1 with the Harder-Matt gate, and you'll get this. And always remember, in bold, I only have the commons. So these commons have no impact on the actual multiplications. There are many other quantum gates. There are the so-called Pauli matrices, X, Y, and Z. They are important in a lot of quantum algorithms, and they somehow transform my quantum system specifically to what I need to do in an algorithm. Like X is just the NOT gate. I said X or NOT is just the same. Y and Z, they do something else. We'll later see that also when we look at a geometric representation of a qubit, then we see what Y and Z actually do. Sometimes these matrices X, Y, and Z are not called X, Y, and Z in the literature, but they are called sigma X, sigma Y, and sigma Z. And there are two other important matrices that are called S and T. What they are doing exactly, again, here, it's not important right now, but they're simply used in various quantum algorithms. And how to build your own quantum algorithm, that's something we'll discuss in my next lecture in 2 weeks. So since next week we don't meet, you'll read the paper on theoretical computer science. We'll meet in 2 weeks, and in 2 weeks we see how we can actually build quantum algorithms, and then when to pick which of these operations. But they're just fundamental operations, like the Toffoli gate, whatever. There are these operations X, Y, Z, S, and T, and Harder-Mudd. They also stay in relation to each other. You can show that the Z gate is the same, like Z is exactly the same as an Harder-Mudd multiplied with an X multiplied with a Harder-Mudd, or an S is a T squared. This is some relations I found in the book. Feel free to try this out. Since they are all unitary, obviously X squared is the identity matrix. Since X multiplied with X, it's obviously, since you look at X and there is, if you apply the adjoint, so the dagger, it just stays X, and then X multiplied by X obviously gives you the identity matrix. You can also show this with Y, where the dagger is slightly more complex, but doesn't fundamentally change anything eventually. Feel free to look at these properties at home or don't. It's just something I found in the book and wanted to put here. Then we have another gate, which is not a unitary gate or unitary matrix. It's the measurement operation. And the measurement operation is a fundamental gate at the end of the algorithm, because once our algorithm is done, we need to turn quantum states into classic states and move that back to our computer outside. And that's what the measurement does. And we've looked into measurement already in the last chapter, and we said measurement adds uncertainty, but turns a quantum state into one of the basic states. Here concretely would be the bits 0 or 1. And the measurement is also visualized in a quantum circuit, often with some sign, something like this, or slightly different, depending on the literature. And that's an AND operation. It's very important. That's not a reversible operation, because if you turn a quantum state and you have it collapse and measure, then you have a definite classic outcome, and you cannot just change this back to a quantum or to the previous quantum state. So it's absolutely not unitary. Then there's a very important concept that is called the Bloch sphere. And the Bloch sphere is something you will also see in the lab session. So soon there will also be a lab problem, which we'll talk about after Horst Kuhnhardt's lecture, because the lab problem only makes sense after he teaches his lecture today. And a generic qubit like psi cat is obviously always a complex amplitude times 0 cat plus a complex amplitude times 1 cat, where we have our general constraint for a quantum state. And it actually turns out, if you know a little bit about geometry, that in complex numbers, that you can turn such a generic state in a different form. You can say it's the cosine of theta times 0 cat plus e to the I times phi times the sine of theta times 1 cat. We just assume this for now. We don't need to prove this. And all possible qubits can be covered when the angles are in a certain constraint. And since we only need these two real numbers, which are these angles, then we can actually try to plot this. We have a 3D plot in order to visualize a qubit. of radius 1, and we call this the Bloch sphere. And sometimes these two angles also have names like the latitude and longitude. You can obviously try to prove this or come up with it, or if you're curious about how to derive this, take a look into the book. But we don't need that in this course. All we care about is the Bloch sphere, and that there's some way to plot our generic qubit on the Bloch sphere. And that Bloch sphere would look like something like that. We have our angles, and we can plot our qubit, which we have here in the Bloch sphere. And the Bloch sphere is a 3D plot, but obviously we visualize it on 2D here. And what we also see in that Bloch sphere is the 0 ket and 1 ket. And then we have our concrete qubit that we visualize on the Bloch sphere. And we can, for example, see if it's close to 0 ket or close to 1 ket. And when we apply various operations to it, like, for example, the X gate, these Pauli matrices I mentioned, you can see how they impact our qubit by visualizing the qubit before and after in the Bloch sphere. So the Bloch sphere is a very good way to understand qubits and these few operations I had just shown before, like the Pauli matrices. And in the lab problem, you will also see how you can visualize the Bloch sphere. The Bloch sphere, there's now a lot of text here that I'm just talking about. So if our qubit is visualized close to 0 ket, and I run my experiment once and I measure, then obviously, most likely I will get a 0 as a classical outcome of the measurement if I'm close to 0 ket, but not all the time. Sometimes it could also return a 1, because as you know, the measurement, and I've said this as of one of the first classes, measurement also adds uncertainty to quantum computing. So if I run this experiment, say 1,000 times, and I measure then each time, probably for a setting like this, most of the time I will get a 0 as the result of the measurement, and sometimes a 1. And that's why I need to run this quantum experiment many times, and then I get a reliable distribution. So the Bloch sphere is a way how I can visualize one qubit. If I have multiple qubits, I cannot just put them in the Bloch sphere, but in the literature, and also if you take a look into some of the books we are recommending, there are sometimes other techniques how you can visualize multiple qubits together, not using a Bloch sphere, but a different approach. And you can do various rotations in here, like a phase change to rotate along one of these axes. And before I mentioned the Bloch sphere, and I said there's also a link to these Pauli matrices. The Pauli matrix actually does a rotation by 180 degrees around the corresponding axis. So we have an x-axis, so we rotate around x. We have a y and z Pauli operation, and there we would rotate around y or z, whatever. And this can all be visualized very easily then, and you see what's the output of these Pauli matrices and the other operations that work on a single qubit. And the big challenge in a quantum algorithm, but that's what we will discuss next time, is in which order, which operations you would apply. So that's the tricky part, and that makes it so difficult to come up with your own quantum algorithm, because you need to find a reasonable way of how to combine these very fundamental operations in order to build a novel algorithm. But that's something we'll see in the next session. So the Bloch sphere can be used to visualize certain dynamics. These slides go quite into detail. If you're curious, read them. There's also a further reading about other rotations on the Bloch sphere, which is explained in the book. Maybe some of these rotations could be needed depending on your seminar presentation, but it's not a must read. So only read it if you want and if you're curious. There are other gates. There's also the so-called controlled U gate. which is sort of the equivalent of an if-then statement. So if a certain qubit like X, the control, is true, then we would run U, and U would be some operation that we could execute if X is true. We can also think about how such a matrix could be represented, but things like that may be relevant to the seminar presentation or not. But this controlled U gate would be just more or less the equivalent of an if-then statement in classic code. And sometimes this controlled, not controlled U is sometimes also written like in an upper index C and then U, so controlled U. And sometimes the C not is also written that way in the literature. So you have a not and a C raised to the upper index. So I said universal quantum gates do exist. And as in classic binary computing, the set of the and not gate forms a set of universal logic gates, and a NAND gate does the two. We can also think about that for quantum gates. Which ones are universal? We said both the Toffoli and the Fredkin gates are both universal logic gates. And we can also wonder, are there sets of universal quantum gates? And the book makes some recommendations that, and it's been proven and it's shown in the book, that the set of these three gates could be a set of universal quantum gates with which you could emulate any other quantum operation, as you can do with an AND and a NOT or a NAND. A set of these three gates would allow you to have a universal quantum gate as well. But that's maybe not too important right now. I just put it here as an information before we spent quite some time on the Toffoli gate, and I think that's enough in terms of universality for today. Now we come to a little bit more theory, and Horst Kuhnhardt, he will be here in maybe 10 to 20 minutes to teach his part, so I can continue a little bit with this chapter. Now we want to get towards quantum algorithms, which is the big focus of the next chapter, and then how to run it on a quantum computer. That's what Horst will teach in between today. But there are some challenges when we want to come up with our own quantum algorithms. And there are actually quite a lot of limitations. So one limitation is all the operations we use, they must be reversible. Otherwise, quantum computing will not work. The only operation we are happy to use that is not reversible is the measurement, because it just makes your quantum state collapse, and that's what we want. And another limitation is the no cloning theorem. And now comes a big limitation, which comes from quantum mechanics. And since quantum computers take advantage of quantum mechanics, we are unfortunately limited by that. So it is impossible in quantum mechanics to clone an exact quantum state. And that's something you really don't have to worry about in traditional computing, because in traditional computing, yes, you have a variable and you can just copy it. But in a quantum computer, it doesn't work that way. The no cloning theorem does not allow you to perfectly clone a quantum state. So it's impossible to make a copy of an arbitrary quantum state. Obviously, say before before the Hadamard gate, if you start with a classical value, yes, you can copy that, but the quantum states, you cannot. You can only try to copy it by destroying it, but you're unable to copy it without destroying it. And that has actually a big impact on computing and writing your own algorithms. in a computer, we are used to copy and paste, say as an end user, but we're also used to copy and paste as a developer, because we can just copy paste variables. With a quantum computer, that is impossible. But what we can do is we can move quantum states, so from one variable to the other. So cut and paste or moving, that's obviously fine, but copying is impossible. So the no cloning theorem is a big limitation, but it comes from quantum mechanics and it's proven. So we are unable to bridge that gap. And maybe you're wondering, what impact does that have on the Toffoli gate and the fan out? This is something I already mentioned before, and I'm just going back a few slides. So just flipping back, where I said we could copy sort of the variable with the Toffoli gate. This works perfectly fine for the Toffoli gate, or with the Toffoli gate, for classic binary values, but you cannot use the Toffoli gate to sort of copy a quantum state. So it only works for binary values, but not for proper quantum states. And that's why I mentioned it already slightly before and said we can do a fan out, but only for binary. Now you see we cannot do it for quantum states. And I think that's something that makes writing quantum algorithms also quite difficult, because you need to come up with some way of writing your code without doing any copy and paste, because you cannot have a perfect copy of a quantum state. And our fan out from before in the Toffoli gate does not violate the no cloning theorem, because it only works for classic bits, not superpositions. The no cloning theorem also has impact, for example, on encryption. It helps to agree on shared secret keys, which is something that is called quantum key distribution. That's a topic that sometimes students pick as a seminar presentation. I think last year 1 or 2 teams picked it, and a year before as well. And the quantum key distribution allows us, or allows 2 parties to agree on a shared secret key. And that's only possible because of the no cloning theorem. Feel free to read about the quantum key distribution in the book. It's explained in the book, or in the Aronson book. So the Aronson book was this quantum computing since Democritus, or what it was called, that I also mentioned in the beginning of the course. The concept or the protocol of quantum key distribution is also explained in this book. So maybe it's something some of you want to do further reading. Then the next concept, and we still have a little bit of time before Horst is coming, because I think Horst wants to start teaching at 4:30. We can already talk a little bit about the next concept, which are so-called mixed states. All the quantum states we have dealt so far with, they're called pure quantum states. And they refer to the fact that our description of the system is entirely quantum mechanical. So a pure state is a state which can be described by a single ket vector, as we have now done for a couple of weeks. But once we have these quantum states, over time, because of decoherence, they may turn into a so-called mixed state. So decoherence is also something I mentioned in the introductory lecture. Decoherence has to do with that over time, our quantum system interacts with the real environment. And once that starts to happen, it loses purity. And the quantum state turns into a mixed state. So the concept of mixed states is that we use classical probability theory on top of our quantum states. So we can something ask like the question, what if we don't know which quantum state we have? And that's why a mixed state is a statistical ensemble of pure states. And we can imagine this as something that we have. So an ensemble could be, we have a half probability of our equal superposition that we already know, 0 ket and 1 ket, and we have the normalizer, the square root of 2, and we have a 50% probability of the other equal superposition that we have dealt with in this course, a 0 ket minus a 1 ket divided by the square root of 2. And before I continue, I want to ask Horst. Horst, are you already here? I saw you have joined. Do you hear me?
Yes, hello.
Hi.
Hello, students.
Because,
I'm here. I'm with you.
Yeah. Because, Horst, for me, it's now a good moment to maybe switch to you. I don't know, can you already take over?
Okay.
Horst will teach now his part about quantum computers and programming, probably around until 6. And I will continue with the mixed states in the next lecture, because now we would only have 15 minutes until Horst wanted to take over, and we are unable to discuss the density matrix. So I'll already pass the floor to Horst, and please go ahead, Horst. You're muted, unfortunately.
Well, thank you, Patrick, for the introduction, and I'm taking over. So we started in the first lecture of mine with the hardware-based realizations of a quantum computer or a quantum gate. And today I want to proceed with that, to repeat again the various technologies, how to build up a quantum computer. And at the end of this block of this part, I will show you some job opportunities in the field of quantum computing. Maybe you realized the news from our German government. So we have a demand in the next years of roughly 10,000 to 15,000 specialists on quantum computing or quantum technology. So I think that's an opportunity. And if you want to go in that direction, I think that's a good basic for a professional career on that. So then let me share my slides. So here we are. So maybe you remember the Di Vincenzo's list, what's about all needed for realization of a quantum computer. And therefore, today we want to finish our implementations overview. So the quantum computer hardware mainly is constructed in the first time of ion traps, then nuclear magnetic resonance quantum computer. So that's a technology that is used in various fields of science and of healthcare management, especially with CT or NMR technology, in order to have a look inside the field of organs, of cells as well. And another promising approach is superconducting circuits. So let's start with the overall architecture of a quantum computer model. So before we apply a quantum computer algorithm on a real quantum computer, we need, first of all, quantum gates. And I think that was the thing Patrick already announced or described in his part of the lecture, that it is very critical to have to reduce noise in quantum computer technology. But first of all, let me ask you, can you hear me good? Can you follow? So if you please raise your thumb or one of the thumbs of your
yes, all fine, Horst.
Is it online? Okay, thank you very much. So and today, I think the direction goes into a kind of coexistence between a classical computer system and a quantum computer chip or a quantum computer system. So I think you all know the numbers, what states are necessary in order to store or to rebuild the states of n qubits. And therefore, I think that's one of the approaches. Therefore, a real simulation or a classical computer, I think that is not manageable and not feasible because of the number of gates that you need, the number of storage, and of course the number of energy that you need for a simulation on a classical computer. Therefore, I'm really convinced that the future in the next years will be a kind of coexistence between classical computer systems and quantum computer. So to go a little bit further on that, what we already discussed in our first lecture. So one of the first implementations worked with nuclear magnetic resonance. So if you work with atoms or with molecules and you bring them into a magnetic field, then the atoms will show some effects. The effects could be producing photons or changing the energy levels, and that is the effect we want to rebuild in a kind of quantum computer system. So we have some static or oscillating magnetic fields, and therefore we want to measure the nuclear spins of the of the atoms or the molecules that we are working with. One of the biggest advantages of the approach of nuclear magnetic resonance, you can use it at the room temperature. And maybe you remember all other implementations needed 0 degree Kelvin, that's roughly minus 273 degrees Celsius. And therefore, there's a lot of technology used in order to get these real low temperatures. Therefore, one of these approaches with NMR technology is a promising one, and there are some implementations with this field. So here the overall technical scheme on that. So you have a glass tube where you have the materials within that you want to analyze, and you use magnetic fields along the z-axis in a liquid where a lot of molecules, atoms are, and the measurement is done by an amplifier and a signal preamplifier, and therefore we can measure the pulses or the radiation that is produced and sent of these atoms. Yeah, the goal is in that following every implementation in a quantum computer, one is if you are able to hold a status of coherence, of entanglement. So we come later on to this term of entanglement, and I will show you some further reading elements. So IBM was successful in getting an entanglement over 27 qubits, and a recent implementation or recent approach was with 64 qubits. So that's a big advantage and a big advance in that field. So the goal is always to have a stable, as long as possible, stable state of undisturbed coherence to do the measurements of that. So the system is as follows: a pulse sequence done by magnetic fields or by radio frequency, energizing the atoms or the molecules or the atoms in the molecules, and the signal is amplified and can be analyzed. So it's the same technology we use in medicine. If you go to an NMR device to have your organs or your body in research. So therefore, the magnetization of the spins is normally too weak to be detected. Therefore, we have to do a lot of measurements with a lot of atoms or molecules, and therefore we want to do as much as measurements as possible, and as long as there is a kind of coherence state of the system. And you know already with measuring, we have a collapse of the wave function, and therefore we need a lot of measurements of these states, and to use probability measures in order to combine the results and to find the best results that is fitting. So here is a very simple example of implementation of the Shor algorithm by Peter Shor. You know, it was one of the first algorithms really developed for the use of quantum computers. And in that test field, there are 7 qubits generated by atoms of a specific type. I don't go into detail for that, but on the right-hand side, you see the spin in bracket form of these atoms. And with that, you can calculate the Shor algorithm for the number 15. So here, as I already said, you need a lot of pulses in order to require the frequencies, or to enable the frequencies. And after the end of the radio frequency pulses, the state of the qubits is measured by this technology we already use, the NMR spectroscopy, that is used widely in physics or in science. Yeah. Another very first implementation of quantum computers were with ion traps, and on the picture on this slide you can see the various states of the ions, and an ion is an electrically charged atom, and these electrically charged atoms can be trapped or fixed in a magnetic field. And you can use laser beams with a certain frequency in order to manipulate the energy levels of the ions. That means doing these quantum leaps from one level to another. And you already know in quantum mechanics or in quantum physics, we don't have a continuously development of the or change of the values of atoms or of energy states. So we have these quantum leaps, as it is called, and therefore we use these ion traps and laser to give a kind of certain outside energy to influence the ions in order to make these quantum leaps. And with that trapped or isolated technical device, we can do our measurements, we can do the quantum, we can hold the quantum states in superposition and entanglement, and therefore we have some time for the for measuring the results. So therefore, I think it is clear that the first 1 or 2 bit qubit gates were implemented with ion traps, and with that, a lot of scientists or research groups work on the scalability of that solution, not only 1 or 2 qubits, so it goes to 20, 30, and so on qubits. So there is a kind of future vision that we need 1,000 qubits in order to do the same things as a very modern high performance supercomputing, and there is a long way until we reach really a stable basis for 1,000 real qubits. So you remember last time we spoke about the company D-Wave, the Canadian firm company that states or claims that it has a 2,000 or 5,000 qubits machine, quantum computer, but we already know the technology, that's an annealing technology, so not quite the same as we introduced here with ion traps or with NMR technology. Yeah, so it is promising to work with ion traps, and some research groups do that. Another implementation is there is a kind of laser or beam splitter used that is called, the technical apparatus is called Mach-Zehnder interferometer. And with that technology that consists of prisms and mirrors, semi-permeable mirrors, laser beam can be split up in two lines, and therefore it is a own field of research that is called linear optics quantum computing. Photonic chips is another term, or CPUs. Photonic CPUs is another term you can read in some papers, and it is another promising approach. Another way that is followed by IBM and some other Japanese technologies is the use of superconductors. So qubits are very single particles. They have nuclear spins, as Patrick already explained, in various directions on the Planck sphere. And the advantage is these nanostructures can today already produced on an industrial scale. And it is a scalable technology. One can use phosphorus, an element that happens very often in the world, and using some impurities in silicium. And therefore, these quantum dots in the nanostructures are based on a mixture of various metals, gallium arsenide or aluminium gallium arsenide, and the size of these quantum dots correspond ideally to the wavelengths of the enclosed electrons. And that technology is a really fast technology, and you can say the quantum dots, they are used today. We can produce it today in big numbers, and we can say that's a kind of artificial atom. So the advantage is we can specify the size, the shape, and energy levels of that artificial atoms, and therefore the decoherence processes of these materials are very promising as a new approach for quantum computing. One example I can show you, that's a qubit that is realized on the spin of a quantum dot with an electron. So the qubits are lined in the form of a quantum dot on a surface, on a semiconductor structure that's widely used in CPU production or CPU designs. And there are magnetic fields that induces the energy splitting. It is called Siemens splitting, and so we can facilitate here spin up and spin down direction, and that's what we need to do quantum calculations. So how could we build these quantum gates? So that's a technology where we can easily build Hadamard CNOT gates and so on. So that's a very interesting technology, I would say, that is used very widely. So superconductors, I already mentioned that physical effect. These superconducting effects arises with a very low temperature at minus 273 degrees or 0 Kelvin degrees. So and with superconductors, we use a pair of electrons that is called so-called a Cooper pair. And in some implementations of D-Wave and other companies, you will find these Cooper pairs, and therefore they use superconducting effects in their designs. Yeah, according to the quantum mechanics, the wave function of a particle in front of a barrier has a kind of probability to stay behind or before the barrier, and this particle can tunnel. So we call it the tunneling effect. This tunneling effect is known very long in chip designs, because maybe you know the chip structures are today shrinking and shrinking, getting smaller and getting smaller. So normally we have 7, 8 nanometer technology in chip design, but technology enables us to go to much smaller dimensions, and therefore these tunneling effects are in normal chip design, as I would call it, something that the companies like Intel, AMD, and so on are a little bit afraid of that effect. But on the other hand, it can be used to produce these very special quantum effects. So tunneling is a very interesting technology that is not really welcome in traditional chip design, but in a quantum computer design, the tunneling effects is a promising implementation. Nowadays, the development goes into a semiconductors development based on metallic or even ceramic basis, and therefore it can be produced on an industrial level, and it is very quick, very fast, and therefore semiconductors are another technology that can be used on a temperature that can be produced in every fridge, a normal fridge, minus 23 degrees Celsius, and that's really very far beyond or away from this minus 273 degrees Celsius, and therefore this semiconductor technology is another technique for implementing quantum computing, and a lot of research groups in Jülich and Münster, Germany, they are working on that technology. So I already explained a bit adiabatic quantum computing. That's another way for finding out local minima, and therefore unlike a logic circuit that is used in normal computer technology, adiabatic means, or another term is heat tight or do not pass through, is a technology that comes more from another domain in technology, and it is related to steel production, to glass production, and uses the mathematics of thermodynamics. So therefore, adiabatic computing is mainly used to solve optimization problems with a global minimum and these local minimums to find is a very special way, and therefore for that problems, adiabatic quantum computing is a really a good approach on that. So annealing is a term that comes from another domain, from the material sciences, and as I already said, it has something to do with the treatment of metals and glasses. And one name, a German scientist in the 1930s, Werner Ising, a chemist, found out that materials that cool down, like metal, steel production, or glass and iron, have special effects. And one used these effects in order to find out what is a local minimum. And it could always be that is another local minimum that we don't see. And therefore, annealing is some technology, therefore quantum annealing, to solve these kind of problems. Again, the technology is used with a magnetic field in order to coupling the strength and the local currents. So each qubit is in that form a superconducting loop, a Josephson conjunction. And I already mentioned the name D-Wave, the Canadian company that announced we have the first available quantum computer. But we know already it is not a universal quantum computer. It is a special quantum computer to solve these optimization problems. Competitors of D-Wave are Fujitsu or Hitachi. So adiabatic computing uses the states of molecules in order to perform the computational operations and store the data. And I have listed some further articles where you can find out more details on adiabatic computing by published in Nature Physics, or in the same article is published in arXiv.org. So D-Wave, a very interesting company, founded 2011 in Canada, and then or founded in Canada, then sold by Lockheed Martin, US company, then the NASA step in, and 2017 they announced they have 2,000 superconducting elements as qubits, and that was a big approach at that time. So nobody could imagine there are 2,000 real qubits that D-Wave produces. And so they step forward, and therefore they always announced more qubits, but we know already that's a annealing, quantum annealing computer. So let's have a look at the timeline of the development, because that's a technology that is started, I would say, really in the 1990s, although the technology or the foundations in physics were laid down in 1920, 1930s. And another very famous name in that field is Richard Feynman in the 1918s, and he's described first the concept of a quantum computer, or of a computer system based on quantum mechanics. So the first kind of realization were, as we already know, nuclear spins in liquids with a lot of molecules, a big number of molecules. The problem is always, how could we stabilize the effect of a superposition of the qubits? And we know measurement destroys always the state of a superposition. Therefore, we have to do a lot of measurements. So in 1997, Neil Gershenfeld from MIT and Isaac Chung from IBM were the first one who realized a quantum gate with 2 qubits, and they used that for solving a search algorithm with a really small number. But it was the first approach on that. The realization was, again, an atomic nuclei in a magnetic field. So the spins, you already know, had 2 values for a qubit, and the changes were done by radio waves in a special frequency, and with a tomography. We already know that for medicine, we measure the magnetic resonance, and therefore there was the measurement on that available. A next big approach was done by Anton Zeilinger, who won the Nobel Prize some month ago. And in Austria, Innsbruck, they constructed the first quantum byte. But it was a big breakthrough on that field. The next kind of realizations were on ion traps. So some research groups were convinced that ion traps, that's the perfect way in order to do a superpositions. But the problem with that approach is the qubits are less robust than qubits made of atoms. And these qubits made of atoms are again less robust on implementations made on quantum dots. So third kind of realization uses superposition and some error detection and error correction mechanisms. And from 2004 on, another line of implementation or realization started, again driven by Anton Zeilinger from Austria. That was the element of teleportation of quantum states over a long distance. And today we use this technology in order to transfer, or in order to do quantum cryptography, in order to secure our systems. So here's some pictures from the first 3 qubits that were entangled. And nowadays, IBM works on the entanglement of 27 qubits and up to 64 qubits. If you are interested, I can share you an article that I found on that. Just a minute. Here is the link. The article is named Generating Whole Processor Entanglement on 27 or 65 qubit quantum systems. Just a moment. So I'll send it via chat, so you can read this article, and that's the latest approach in entanglement of 27 qubits, and we call it the Bell state in order to do a Bell state is the description of an entanglement of qubits, and here is the description how IBM started with that entanglement. And on this slide, sorry, I have to do another screen sharing with you. So now you should see the article. So here is the title of the article. I already mentioned generating whole processor entanglement on 27 and later on 65 qubit quantum systems. And I wanted to show the figure on the various technologies and how far IBM is on that field right now. So with superconducting approach of IBM, they are able now to entangle 27 qubits, and here on the x-axis you can see the timeline and the various approaches. So ion traps were the first implementations. Then came photonic implementations. Then neutral atoms or quantum dots technology, and with that technology of superconducting, IBM uses in this approach, in their approaches, they are able now to entangle 27 elements, 27 qubits. And here is the combination. You already know that's the combination of a Hadamard gate and C0 gate. And with that combination, you can implement an entanglement. And with an entanglement, algorithms in quantum computing are much easier to be implemented and easier to be measured as any other approach, and therefore that is really promising with that technology. So you can read the article directly in the chat, and then I go back to my slides. So very long development on that. It is an aluminum container that was produced, and the quantum chip is right here directly in the middle, and all this technology is used to get the environmental conditions in order for having a near vacuum, this very low temperature, and the diameter of this quantum chip that is called is roughly about 40 millimeters. Today we are in much smaller dimensions. And here is an example of D-wave. If you want to follow the link or to go to a video, you can have a look inside these cabinets. And here is a man. So it is a kind of 3-meter high facility where the quantum chip is really inside, and all these cooling elements are around this quantum chip. So in this lecture, Patrick will introduce some programming technologies with you and the math behind that. So there are some approaches or various approaches from the companies producing quantum computer systems. So first of all, IBM, Google, or other big companies. And one programming environment, more a Python-like software library for, again, writing and manipulating quantum computer software. And this programming environment with a complete library is running on quantum computers or quantum simulators, where you can check out the way how to program a quantum computer. So let's go a little bit back in time. How was the state in 2017? So the quantum simulators are one of the approaches that is used today, that are used today. And the prototypes at that time were atoms in optical grids and the alignment of ions in ion traps and laser pulses in order to raise and to lower and to do the measurements on the system directly. Some names should be dropped in that field. The University of Innsbruck, again Austria, and the Max Planck Institute of Quantum Optics at Garching. And from that Max Planck Institute, in the last Nobel Prizes were won by one of the scientists of this Max Planck Center. So another milestone was initiated by or announced by Google with the 53 qubit system, and IBM was at that time only a 50 qubit system, and therefore is always the fight or the race between IBM and Google. And on the other hand, that is more dominated by US companies or Asian companies in Japan or in China. And the European Union wanted to start a quantum computer system too. So until 2021, we have 2023, they wanted to reach the goal of a 100 qubit system as a quantum computer operating system. You can follow the website on that link, and the European approach is far behind that goals that were set in 2018. So here is a look inside the IBM first approach. That was the 5-qubit system that was offered in the cloud to be used in various fields of universities, in teaching, in research, and IBM called it the quantum experience platform. And here all these lot of wires are indicating or used for cooling down, for measuring the system, but really in the inside, in the middle, is the small quantum chip. 2019 was one of the breakthrough years, I would call it, for the IBM Q system one, and one of the first systems of IBM was were installed at Ehningen, this next to Stuttgart in Baden-Württemberg, and that was this 27 qubits system. You can rent it if you have the money for a lot of money, but IBM offers some 3 minutes or free time in order to use this quantum computer system. So the quantum computer chip here inside, and here is another picture of the inside of this system, Q system. It's a kind of Faraday cage and cooling technology. The glass material absorbs radio frequency, and IBM is able to hold to coherence time over a really long time in that field of 75 to 100 microseconds, and that was a big success in that time. And IBM is working further on that technology, and as we read in the articles, now they work with 27, 65, and even more qubits, and to reach this state of entanglements. Here again, some web links if you are interested in more details on the IBM technology, and interestingly, the keynotes of Dario Gil, Vice President of the Research Director of IBM Research. And on this platform, quantumcomputingibm.com, you can produce your own test equipment in order to work with that quantum computer and to program your first quantum computer software. The software or the development kit is named QISKit, that stands for Quantum Information Science Kit. So we have a simulator and some subsystems in order to reduce the noise, because noise is always one of the problems in doing the measurements and in all the systems. Then therefore we want to they all want to produce a safe atmosphere, safe environment in order not to disturb the state of coherence of that. And with QISKit Aqua, a library of some quantum algorithms are available. The other big competitor of IBM is Google, and Google has produced this Sycamore approach. And John Breskill, one of the scientists, always stated this so-called quantum supremacy means that a quantum computer can solve a problem much faster than a classical supercomputer. And sometimes there are some artificial tests in order to have this quantum supremacy. But if you read this your article, you will find out that the algorithm or that kind of problem is a really artificial one, and therefore there is always the fight and the race between the classical design, the classical approach, and the quantum approach. The old race, IBM and Google. But Sycamore is a very interesting chip design. On a 1 centimeter microchip surface made of aluminium and indium, they were able to realize 54 qubits. And therefore, these microchips again need an operating temperature nearly absolute 0 Kelvin. Therefore, you need all this cooling and so on. But the technology is a stable one, and therefore also one approach Google follows with this sycamore implementation. So again, in the beginning of my part of the lecture, I claimed that in the next years, we have the coexistence between classical computer, high performance supercomputer, and quantum computer. And therefore, simulation and coexistence, I think that's one of the things, one of the developments that we will face in the next year. Interestingly, at Jülich, our research center, big research center in Germany, at that time, supercomputer Eugene was simulating a quantum computer with 42 qubits only. So remember, 42 qubits only. So the simulation software runs on many computers, and these Eugene supercomputer simulates at that time the world's largest quantum computer system, and so there was a need of 300,000 processors with a performance of 1 quadrillion computing operations per second to simulate a 42 qubit system. And therefore, you can imagine you need a lot of classical computing power in order to do a quantum computer simulation. And therefore, I think the direction goes exactly in that field, that on a classical computer, the typical problems where classical computers are strong, they should be solved with that. But there are some problems like optimization and all these type of problems that could be used with a quantum computer. So here is an image of the sycamore approach from Google. And here you see the Google boss on that. So there is not only IBM and Google and other big names. Another big name is Amazon, of course, and Honeywell, well known in computer technology. Rigetti at Berkeley with a 31 qubit system. IonQ, very famous company, and Chinese companies and Canadian company that works with photonics and with computers based on photonics. So here is the link to the website of the already mentioned Max Planck Research Center, and I choose this slide in order to introduce some names on you. Professor Hensch, that was the invention, the development of Professor Hensch, and he is now working at the Max Planck Institute, but he was the one who did the miniaturization in hard disk systems at that time, and some other famous names in that research center. The other center of research is based in Austria. Professor Zeilinger moved from Innsbruck directly to Vienna. Now he is retired, he won the Nobel Prize, but he is still working in his research group on the field of teleportation and some other really breaking technologies in quantum computing, and he is one of the big names in quantum technology. Interestingly, professor from Austria. And some other places where research is done in Germany and in Europe. So Fraunhofer, you know, very famous research company, and some other projects here. And a link to the European quantum flagship program. Very interesting study was done by Bitkom to address a bit the German quantum ecosystem, as it is called. I want to start or to share this link with you. So I have to change my screen. Here we are. So Bitkom is an association of computer manufacturer, computer companies in Germany. They do a lot of applications, they do a lot of guidelines, and so on. And therefore, it is interesting to read something about the German quantum ecosystem, because at the end of my part today, I want to give you some hints, a glimpse what fields of technology or what fields of business and research can be used with quantum technology. And therefore, I think it's good to have a glimpse on the companies in Germany who work with quantum computing or do research on quantum technology. And that's surprisingly a lot. So here you can download the complete study or the complete program, but I want to go or to show you the list. So Alpine Quantum Technology, they have a quantum simulator and also use open source and grants a public access to that. Then Atos, simulation on quantum computing. Amazon, D-Wave already mentioned, Fujitsu, Google, Hitachi, Honeywell, Intel, VMware, and Terra Quantum, all names where you can establish contact if you want, and to check out what they are doing in the field of quantum computing. So that's something called as the German quantum ecosystem. And as I already said at the beginning of my part, there is a recent announcement of the German government that in the next years we will see a demand of 10,000 to 15,000 specialists on quantum computing. So what job opportunities can be reached with knowledge in quantum technologies? I think the main companies or domains in that field are all areas or all companies that are working with a really big amount of data and doing simulations, solving optimizations problems, and therefore airlines, banking, finance, chemicals industries, healthcare, of course, life sciences, and all research companies in that field using now and will use in future quantum technology. So therefore, in the field of technical services, what do you need? So an overall technology knowledge on that domain. Then in the field of application development, Qiskit and programming technologies. In the field of consulting or use case specific fields, performance libraries, compilers and operating systems. That was the European project. Of course, we need an operating system in order to do the management of the various hardware components of a quantum computer. And even though in the field of an assembly language, there are some approaches where quantum computers can be programmed with an assembler-like language, and the development of quantum computing hardware. But I think that is more the domain of research field in engineering, in chemistry, in physics, and all to do this development in quantum technology. So what will be the future, or how could a processor look like in the future? Maybe we have an Intel chip in the future that is with the symbol spins inside, or quantum pro processor. I think that could be one direction where the development goes, that we have coprocessors or coprocessing solutions in the combination of classical computers and quantum computers. But I think there is still some development to be done in the field of a real time or real world classic computer. Yeah, I have some further links for in the field of quantum computing. There is a simulator here in the first link. Then quantum computer, Google, some film some video about the quantum computer technology. Then again, the access to the D-Wave systems, cloud system, and the quantum computing simulator system that runs on, or the quantum computer access that runs on this German computer system installed at Ehingen next to Stuttgart in Germany. So that was the thing I wanted to share with you today. And at the end of the lecture, you should be able to distinguish the various hardware implementations of a quantum computer. You should remember DiVincenzo's list. What is a real quantum computer? You should be able to explain what is the difference between, I would say, real quantum computing to adiabatic quantum computing, and answer the question, is the D-Wave system a real quantum computer, or for what problem is it able to solve? And to find out, I think, your position in the field of traditional computer technology, quantum technology, and maybe you can find out the kind of job perspective for your future, for your professional career in the field of quantum technology. So the next lectures will be held by Patrick, and you go a bit deeper. Sorry, you go a bit deeper in the mathematical background, complex numbers, matrix manipulations, quantum gates, quantum circuits with Patrick, and at the end you will work with Jupyter notebooks, and you can do and produce and program your own quantum computer programs. So we will meet each other, or meet virtually at your presentations that are scheduled for January, and I will be in December with you in the December meetings, where you present shortly your idea, what you want to work on, or what you want to present for your seminar papers or your study papers, as you will call it, in January for this elective. But now we have time for some questions. if you have one, some questions. Yeah, if that is not the case, then I wish you a nice evening and interesting and good lectures with Patrick in the next time. And I will give over to Patrick for finishing this lecture.
Yeah, thank you very much, Horst. So there's also a lab problem, but I'll say more about that in the next session. As I said, the next session will be in 2 weeks. Next week, read the paper on theoretical computer science, and we'll continue in 2 weeks. I guess I'll finish the content in 2 weeks. I will be done then, and then in early December, we'll have your topic proposals. I'll also say a few words about that in 2 weeks, and then we'll meet again in January for the seminar presentations. Have a good evening, everyone, and take care.